Hey there, class. We're here today to look at drawing a free body diagram. Now, a free body diagram, you'll hear me often just say FBD for short. I've heard these also called force body diagrams and some other things, but I'm going to call it a free body diagram. And a free body diagram basically is the picture we draw when we are going to solve anything that has to do with dynamics. That would be forces. So a couple quick things here to note. What we need to remember, some red flags to look out for and so some things to remember. First of all, that force is an interaction between two objects. A force is going to always involve two objects, only two objects, and never more than two objects, never less than two objects. Okay, so the important thing to remember here is that it's always two objects. Okay, another thing I want to point out, a red flag to look out for, is that force is not the same thing as motion. When you think motion, you should be thinking speed or velocity. Okay, so I don't want you to think force whenever you when you hear the word motion. Now, do forces and motion, are they related? Absolutely, but the force itself is not motion. Next thing that I want to point out that's a red flag to look out for is that there doesn't have to be force for something to be moving. Now, I know this may seem counterintuitive to you, and the demonstration or the illustration we're going to use here in just a bit is going to kind of show you that. And again, notice I'm saying here in the present tense, okay? That means right now at this moment, there's an object moving, doesn't necessarily have to have force. So to actually illustrate that point, we have two situations here. One where we have some kind of cart moving across, and I apologize that it's not very straight, but we're going to pretend this is a nice horizontal surface that this cart moves on. Notice it does have a velocity. Keep in mind that our velocity is, we are talking about the velocity of the center of mass. Remember, sometimes we're treating these things as what we call a point object. So we treat all of its mass to be here at the center of mass. And let's take a consideration to the second object. Notice this one has a velocity of 0. So in other words, we'd say this one up here, situation number 1, has motion, and situation number 2 has no motion. It is not moving. Now what I'm going to propose, and it may not seem initially intuitive, is that both of these have the same dynamic quantities to them, or the same dynamic situation. Dynamically speaking, these are equivalent to one another. And I'm going to show you that through the use of something called a free body diagram. Okay, so to start this out, what we're going to look at here is the first thing, I guess maybe make a couple notes, is that because we're treating our object as a point mass, when I draw my free body diagram over here, I'm also going to consider all the forces to be acting at the same point. Now, certainly if we wanted to get really picky about this, we could understand that this is probably has 4 wheels on it. Each wheel is going to experience a force. And, you know, certainly we could do that, but we're going to try to simplify things down and treat them all as point masses. Later on this year, we will deal with rigid objects when they have forces that, you know, that are at different locations on there. But for now, let's treat this as a point mass. So to start off my free body diagram, I draw my center of mass, my center of gravity, and I ask myself, what forces do I feel as this cart? Now, one of the first things I would say is I feel a force downwards. Okay, there's a downwards force here. Let me see if I can draw that a little bit straighter, but there's a downwards force, and we basically know that force, because again, I think we can safely assume that we are here on Earth, and this would be a force on the cart by the Earth. Commonly, this is known as the force of gravity. Okay, so a couple real quick notes here. First of all, when I write here in the parentheses, this is what the force is on, and this is what it's by. This is what causes. The cause of this force is the Earth. Notice a couple things here. If we go back to what we thought about in the beginning of the lesson, the force is an interaction between two objects. Notice there's two objects involved here. There's the cart and there's the earth. There's no more than that. And this is what I refer to as on-by notation. This is going to become especially important when we deal with Newton's third law, but for now that's outside of the scope of this particular video. All right, so continuing, one thing I've just added here is that we are not accelerating. This object is simply moving and there is no acceleration. Of course, we are ignoring air resistance and friction, and so therefore, when we talk about this, this cart, we say, well, what else do I feel? Well, I'm going to feel something pushing me up, and as the cart, I feel that upwards force, so it's a force on me as the cart. Cart starts with a C, about that. Cart, and what pushes me up? Well, it's the ground. It pushes me up. So the force is on me as the cart, and it pushes on me, it's by the ground. Okay, so on cart, by ground. So again, on by notation. In shorthand notation, we are going to call that the normal force. Okay, normal. A normal is simply a word that means to be perpendicular to. And you'll notice that that is perpendicular to the surface. So this is actually the completed free body diagram of this particular situation. One thing I can note here is that the acceleration is 0 meters per second squared. These two forces have to balance out, and Newton's second law tells us a little bit more about that. Again, that's for the some future videos, but for today, we're just looking at how to draw this free body diagram. Now, it may bother you that there's no force to the right, and that's a very valid thing to think about, because certainly for this object to be moving, something must have pushed it at some point in time, and I don't dispute that at all. So let's think back into the past where this cart was over here, and maybe it was sitting on this ground, and something did in fact come and push it. So there'd be some kind of force here on the cart by some unknown object. Could have been a gust of wind, it could have been somebody pushing it. It doesn't really matter. The point is there was some kind of applied force some time ago. But the reality is we don't really care about that. We are looking in the present tense. What is happening right now at this moment? Right now it's moving and there is no acceleration. So therefore, our free body diagram is complete when we have these two forces acting on it. Now, what I'd like to do next is I'd like to take a look at our second situation. I want to show you how this is actually dynamically exactly the same. Okay, so once again, I put myself in the place of this cart, and I say to myself, all right, what do I feel as the cart? Well, I'm going to feel that force of gravity pulling me down. Okay, so it's pulling on me as the cart, on me, by what? Well, the earth is what causes gravity. So the earth has an attraction towards me. Oh, and I guess I should note this, that the things we put in here are always objects. Okay, they are always objects. The cart is an object. The earth is an object. Okay, we don't put ideas in there. These have to be they have to be a thing. They have to be an actual thing because, again, the force is in an interaction between two objects. Okay, objects are real things. All right, next, as I sit here on the, I sit on this horizontal ground, something's gonna have to push me up. If there was nothing pushing me up, I'd be falling down. And we certainly understand that putting a cart on a table or a ground, it's not gonna just fall down. So we're going to have an upwards force. That was nice and straight. And that upwards force, again, is on me as the cart. Keeps misspelling cart, I don't know how to do that. It's on the cart by, what is it by? Well, the ground is what I'm in contact with. Or maybe a table. Again, I said the ground, I guess, so we'll just stick with that convention. And because these two are in balance with one another, our acceleration, once again, is 0. And so if we compare these two free body diagrams, these are the completed free body diagrams, we notice they are 100% identically. the same. Dynamically speaking, these two situations are the same situation. When it comes to the kinematic side of things, though, we know that this one's moving and this one's not. But when it comes to simply forces, these actually have the same forces acting on them, and forces have to do with how it accelerates. So we notice that acceleration-wise, these both have the same acceleration. So to summarize what we do when we are dealing with a free body diagram, one thing you want to ask is what is currently interacting with the objects. And again, when you hear the word interacting, you should be thinking force. Forces are always due to one object interacting with another object. Two objects, never more than two objects, never less than two objects. What direction does this force push? Okay, we draw that with the arrow, of course. And lastly, how do the magnitudes compare? A vector that's this way is going to be larger than a vector that's that way. So we draw them with a correspondingly different magnitudes depending on their lengths or their magnitudes. So the vector here on the top is bigger than the vector here on the bottom.